so that I don't mess up again. And my clock says it's after 9 o'clock. So since you have to leave early, I think we probably ought to get started.
All right.
And then that way you can ask your questions at the beginning, and if there are particular problems, we can cover those before you have to go. So I'll, let's see, by way of introduction, this is CHEM102 Chapter 13 review on equilibrium. And so I'll open the floor for your comments or questions, and we'll deal with your concerns right away.
All right.
If you have any. Oh, there's somebody. Kessa. Okay. So we got Steffi and Kessa. That means we're only missing 3. We're going to go ahead and get started. And if you think of anything that's really pressing on your mind, interrupt me. There's Isaac.
I'm still having trouble with my Cengage. I'm not able to access my homework. Like something about where I bought Cengage last semester, and I forgot that I was going to need Cengage for this semester, so I was going to have to rebuy it.
Yeah.
I paid for Cengage, and then something happened with Cengage, and Cengage refunded my money back to my debit card, and then locked me out of my Cengage account. So I've been emailing them for 2 days, and apparently they're supposed to fix my Cengage account and take the money back out of my debit card and repay for it and everything.
Yeah.
But I had to talk to the school, make sure there was nothing wrong with my school email, but I can't access my homework at all. So that's why none of my homework's done.
Who are you emailing?
I was emailing technical support with Cengage.
Okay. Do you still have?
Because it was faster to do it than talking on the phone.
Do you still have the email for their representative?
Mhm. Yeah, it's in my. I've got it on my personal email because I couldn't do anything with my school email. But she said it should be fixed at some point in time this week, and that was yesterday or the day before, something like that.
Oh, so you did contact her?
Yeah, I got a hold of somebody, and somebody said that they were supposed to go back in and reset my entire Cengage account and all of that. So, all right. I don't know what was wrong with it. She said they had like a couple complaints about something about where it was City National, something about City National debit cards. They were having a whole bunch of problems with it. So I don't know, but I paid for it, and it let me do my Chapter 10 homework, and then it locked me out of it completely, and then refunded all the money back to my debit card, so I don't know what happened to it. But I don't like technology.
No. I may have to consider an alternative for next semester.
Yeah, because I had trouble last semester too when I bought my Cengage, remember? And it booted me out with my debit card. I don't know if it's because I have City National and it's just the type of debit card that I have, but I don't have any other way to pay for it, so it's my debit card or nothing.
Oh, you don't have a credit card of any kind?
I have a credit card, but I won't use my credit card for stuff like that. Like it's like for gas and stuff. I don't know.
Okay.
But that's why. But hopefully she'll get it fixed today or tomorrow, and I'll be able to work on my homework this afternoon or this weekend.
Okay.
So that's why my homework's not done, just in case if you were wondering.
Yeah, I'm not going to impose any penalties, but I just don't want you to fall too far behind.
I won't. I can send you a screenshot of the emails and stuff from me and the Cengage representative lady. Or man, I don't know if it's really a man or a woman. It's an email.
Okay.
But I can send you pictures of my email.
Do that, and I'll contact them too.
Okay. Quit.
Okay, let's see, who was it? Heather. So we're missing Megan. No, wait a minute, there she is. No, that's Heather. Yeah, we are missing Megan. Okay. This is one of those situations, it's kind of like if you don't want it to rain, take your umbrella with you. So I just told Steffi that we were going to get started, and then everybody started showing up. So, it's magic. All right, we really will get started now on Chapter 13, Equilibrium Review. So everybody got your review document in front of you. And we'll just start at the top. This is a really short review document, so I don't think we'll have any trouble getting through it. And then I've identified 2 or 3 other problems that are not in the review document that I thought might be helpful. So we'll get to those as well. I'm pretty sure we'll have time for that. All right. So let's start at the beginning. So number 1 is sort of a logic question. So if you're considering the equilibrium of that gas and this solid yielding this gas. First of all, what type of equilibrium is that? Is it homogeneous or heterogeneous? Well, it's obviously heterogeneous because you have a gas solid phase together. Now, what do we need to consider for this equilibrium? We only need to consider the gases because the solid concentration doesn't change. Right? Solids and pure liquids are not part of the equilibrium expression because their concentrations don't change while the system is coming to equilibrium. So let's see what the question is. That's always important. Which of the following statements about the equilibrium is false? So that implies, since there are no answers in here that say 2 of the above or none of the above or any type of that, then that you assume all of them to be true and you find out which one's false. So if we start at the top, for A, what happens if we apply heat to this equilibrium situation? Well, the only reference I've given you to heat is exothermic versus endothermic. And if it's endothermic, the heat factor goes in as a reactant. And if it's exothermic, the heat factor comes out as a product. But we're not given that information here. Right? So we've got to go back to theory. And the applicable theory here is collision. Right? So the collision theory says that you're going to get more collisions and more potential reactions if the temperature is raised. Another way to look at it is if you add energy to the system, if you add heat, then you're going to reach the activation energy or exceed the activation energy. All right, so if we do that, then the first answer says that the right side, the product, is favored. Well, let's see if that makes sense. Based on the collision theory and exceeding the activation energy, we would expect that with more collisions, you would get more product. So with the limited information we have, the only logical conclusion is that this is true. Now, if it turns out that this reaction, if we were actually given whether it's exothermic or endothermic, then we could use the Le Chatelier approach. Okay, so we're going to say that A is true, and B is it's a heterogeneous equilibrium. We already covered that one. That's heterogeneous. And C is if the pressure on the system is increased. If we increase the pressure, what happens? By changing the volume, that means the volume would have to be decreased. Okay? That's just Boyle's law. The left side is favored. Right? So let's see what happens when we decrease the volume and increase the pressure consequently on a gaseous system. Any system that has gases in it will potentially respond to a change in volume. So you only have to look at the gases, and we find that 2 moles are in the product, whereas 1 mole is in the reactants. So if you increase the pressure by decreasing the volume, you favor the side with fewer moles. So in that case, we favor the reactant side. And let's see if that's part of the statement. The left side is favored. Now again, when we say left and right, if we don't have a balanced equation to reference left and right, then left and right means nothing. So we have to have that reference in order to say left or right. Otherwise, you say reactants and products. And in that case, I guess technically you would need a balanced equation as well. Because if you're going this way, that's the reactants. If you're going this way, those are the reactants. So you still need an equation to reference. That one's true. Let's see what D says. Adding more hydrogen gas increases the equilibrium constant. So if we add hydrogen, we increase K. That goes back to the definition of K, right? K is a constant. The only thing that can change K is what? Temperature. So as long as we keep the temperature constant, and we have to assume that, if you add hydrogen to that, it's not going to change the equilibrium constant. However, it will change, and this is not part of the question, it will change the equilibrium position. Because if you add hydrogen, some of it's going to be consumed to produce hydrogen iodide, but it won't all be consumed. So your concentration will change, only the equilibrium constant will not change. The position will change, but the constant will not. So this one's false. The K does not change. Okay, so we found one false one. Let's see, removing HI as it forms. So we're going to remove HI as it forms. And what should we expect? The equilibrium forces the equilibrium to the right. So we favor product. Is that true? According to Le Chatelier, that's true. If you remove this, you impose a stress on the system, and it responds by producing more HI. So that one is true. All right, so we only had one false one. All right, that was D. Okay. Those are going to end up on the floor if I'm not careful. Okay. See, I moved it around and got some shine. Move it back. There we go. Okay, number 2. For number 2, the question is, which of the following statements is true? And we have 4 statements, and then E says 2 of these. So it's possible that more than one is true. In fact, 2 may be true. So we look at each one individually. Which of the following is true for a system whose equilibrium constant is relatively small, which means it would be much less than 1. So we got a small equilibrium constant, and we want to see if which one of these statements is true. A short time to reach equilibrium. Okay, here's the giveaway. Time. Equilibrium says nothing about time. Now, underlying equilibrium, we know that reaction rates have something to do with it, but the equilibrium move itself says the constant doesn't say anything about time. Even with a small k, this reaction could go quick, or it could go forever. It could go essentially to infinity. Nothing about time. So B is also false. Right? Says something about time, doesn't apply for equilibrium, the equilibrium constant. So what does C say? C says the equilibrium lies to the left. Right? So if it lies to the left, we have to invent an equation. Okay, so if that's our equation, and the k is small, and I'm going to abbreviate this to products over reactants, rather than write in all the terms. This is all we need to know based on the k. So if the k is very small, which does it favor, products or reactants? Well, it means that this is very small and that's very large, relatively speaking. So if a k is small, we're favoring reactants, large, small. So it favors reactants and lies to the left. That's true. Okay. D says it lies to the right. Right. They can't both be true. Right. So, as it turns out, E doesn't apply because only one of them is true, which is C. Okay, I'm going to make some more room here. That should be enough. And we'll look at number 3 for the equilibrium system. So we got to write their system first for number 3. Then we can say something about it. Carbon dioxide and hydrogen yields. That's a gas. That's a gas. And carbon monoxide is a gas. And water is a gas under these conditions. And the delta H is what? Is a positive 42 kilojoules per mole. That's our system. And let's see, is it balanced? 1 carbon, 2 hydrogens, and 2 oxygens. Okay, we're good. So we're also given the K. K is equal to 1.6. Okay. And again, no units. We don't put units behind the K. Initial conditions before the questions are asked. 0.15 mole each of reactants and products. Right, so 0.15 mole of each is introduced into a 1-liter container. Right. So we can say that the concentration to begin with is 0.15 molar because the volume is 1 liter for everybody. Okay, and the vessel, in an insulated vessel at 1260 K. So we're given the temperature is 1260 K. Now we've extracted all this information so that it makes sense. Word problems are not meant to make sense. They're meant to deliver information and ask questions. But the only way to make sense is to extract the information and put it in a logical form in front of you on paper. Then you can see what you've got and look at the questions and see you may not need all that information. Okay, so as the system comes to equilibrium, we've got these 5 questions. They include 2 things. One is what happens to the temperature. It either decreases, remains the same, or increases. And the mass of CO2 would increase or decrease. Those are the only 2 options. Right? So we want to see what happens to CO2 in this process. The question actually revolves around which way is the system going to move to reach equilibrium. Right? And if you're given the K and you're given initial conditions, a light bulb ought to go on. What's the Q? Because then if you calculate the Q, you can compare it to the K and you know which direction it's going to move. Right? This one's not one of those simple ones where one of the values is 0 and you just automatically know it's moving that way. In this case, you have to actually calculate the Q. So we need an expression for the K so we can calculate the Q. So the K is equal to carbon monoxide, water. Unfortunately, all the coefficients are 1. There we go. So Q then would equal 0.15 in each one of these, right?
Dr. Bly,
Yes.
I just got an email from Cengage, and she said I should have full access to my Cengage now.
Okay, good.
So it
Who-
should be fixed now.
Who sent you the message?
It just says Cengage tech support at Gmail.
Oh, okay.
Yeah.
Whoever's on staff at the moment.
Yeah, whoever's on staff, but it says I should have access. So I'm gonna log in really fast on my phone and see if I can access it.
Okay. In the meantime, we'll continue with this problem. Okay, so I went to the trouble writing all this stuff up here, but you probably already knew that that times that divided by that times that is equal to 1. Right? Right. So if that's 1, that means Q is less than K. Right? So if Q is less than K, which way is it going to move? Right? K is more than 1, so it favors this side. So if Q is less than that, that means you've got, you don't have enough product. Right? If Q is less than K, that implies that you don't have enough product for an equilibrium situation. So it needs to move to the right. Which means, in terms of answering the question, what happens to CO2? Well, CO2 decreases, right? So we know that. And then the other part of the answer is what happens to the temperature? Well, if we're not maintaining a constant temperature and we let the temperature vary based on the reaction, then you look at delta H. What type of reaction is this? With a positive value, that means it's endothermic.
I have access.
Okay, good. Excellent. So it's endothermic, which means it absorbs energy from its surroundings, and the temperature of the system has to decrease. So CO2 decreases, temperature decreases. And that means B would be the answer. Temperature decreases, and the mass of CO2 would also decrease. That's B. Okay? All right, that was 3. How are we doing on time? Okay. Let's see, 4, 5, and 6 reference a theoretical equation. They're all gases. So let's see. We're going to reference 2A, 2B, C. 2A gas plus, so it yields 2 B's and a C. I think that's right. Yeah, and the K is 1.6 times 10 to the 4th. So 1.6 times 10 to the 4th tells you right off that products are favored, heavily favored. In fact, this reaction goes almost to completion. Okay, so 4, let's see what the question for 4 is. The addition of chemical B to an equilibrium mixture of the above will what? So if we add B, what happens? Well, if we add B in its equilibrium, we don't even need to know that. The reaction is going to shift to produce more A. Right? So the only one that fits there is A increases. A increases, and that turns out to be the A choice. For 5, at a higher temperature, K is 1.8 times 10 to the minus 5. So if we increase the temperature, then K becomes 1.8 times 10 to the minus 5. Right, so increasing the temperature says that now reactant is favored. So if we do that and we favor reactant just by increasing the temperature, then A is going to increase, B and C are going to decrease by doing that one simple thing. So it's saying that B increases. Place equal mix. Oh. All right. So I didn't read the question completely. At a higher temperature, K equals 1.8 times 10 to the minus 5. Then placing the equilibrium mixture in an ice bath, lowering the temperature will what? So the implication is that we've already established equilibrium at a higher temperature with this K. Then we reduce the temperature with an ice bath. Okay. So now what are the same choices? A increases, B increases, no effect. Can't be, we definitely can determine what's going to happen. So at this equilibrium, we've established a situation where we are, okay, at this new equilibrium, we have almost no B and no C. We're higher temperature. If we lower the temperature, we're saying that we're moving away from this K toward that K. And when we do that, we favor the formation of products because this is a higher K than that one. Does that make sense? I need to say it again. Yeah. We're going from, by doing this, we're moving toward, let's see, this is K1, this is K2. We're moving toward K1 conditions, which favors product. So B will increase. And that's B increases, which happens to be B. Okay, 6, raising the temperature by lowering the volume of the container. Raising the pressure, excuse me. Raise the pressure by lowering the volume. Okay, so we're going to do that again. Increase the pressure by decreasing the volume. So we've got gases here. And if we increase the pressure, we're going to favor the side with fewer moles. Right, you have 2 there, 1 there, and 2 here. So that's 3 versus 2. 3 versus 2, we're going to favor A. So we should, A increases. Now, they didn't tell us which situation we're in, this one or that one, but it doesn't matter. If we're at equilibrium and we change the pressure by decreasing the volume, the effect is going to be the same. Moves that way to the fewer number of moles. So A increases, and that's the A choice. Okay? All right. Let's see. I've already used up a half hour. I'm going to save 7. I'm going to move to 8. So here's our system. We've got this complex ion. A complex ion is usually a central metal with several ligands attached around it. And in this case, the ligands are water. And the color is pink. So we're going to be able to tell what's happening in the reaction simply by a color change. And if we add 4 chlorides, then we get blue and 6 waters. All right. So now we have this equilibrium situation. Which statement below describes the change that the system will undergo if hydrochloric acid is added? So if we add hydrochloric acid, these are all aqueous, by the way. It's a dead giveaway because you got water there and water there. So if we add hydrochloric acid, what are we actually adding that's common to the reaction? The common ion is chloride. So we're adding chlorides. Right? So if we add chlorides, what's going to happen? Well, we have choices. More blue. Is that true? Should be, because the equilibrium system is established here, and we're adding reactant, so we get product. Let's see. Let Kessa back in. There we go. Did you have to go outside to get a signal?
No, my birthday's tomorrow, and my boyfriend's paying to have my car detailed, so I had to drop it off, and my mom called me, and it kicked me off. And I kept telling her, I'm like, Mom, I'm in the middle of class. I have to go. She's like, well, I need to know where to pick you up. So that's why.
Okay. So adding chloride ions will, the stress to the system is on the reactant side, which will make more product, which means it will become more blue. So that one's true. B says it should become more pink. They can't both be right. That one's false. And C, the equilibrium will shift to the right. Shift that way. That's true. Actually, I shouldn't do that. We're looking for the true ones, aren't we? So we got this true one and that true one. And then D, shift this way. Can't both be right. It's got to be one way or the other. And then E says 2 of the above. That's true. We got these two. So E is the answer to 8, simply because A and C are both true. All right. Yeah, let's do number 9. We'll do 10 also, 9 and 10. So here's the equilibrium system that we're dealing with. Hydrogen gas plus some other diatomic gas yields that gas plus energy. Okay, I think that's balanced. Yeah. 4 hydrogens, 2 of these, and 2 of those. Yep. Okay, now the question, number 9. Addition of X2 to a system. So we're going to add reactant. We'll do what? Well, if we add reactant, we're going to shift to the right, which means that any hydrogen gas that's there already, part of it will have to be consumed in order to reestablish the equilibrium position. So A is true. A is true because this one decreases. Let's see. Well, D can't be right because it says no effect. E cannot possibly be carried out. That was just, I needed an E, so that was the least offensive one. X2 decreases. Addition of X2 to the system. All right, let's look at that. X2 decreases when we add X2 to the system. Well, based on its equilibrium position, you have a certain amount of X2 to start with. Then you add X2 and force the system to the right. But does it consume all of the X2 that you put in? No. So actually, when equilibrium is reestablished, you have more X2 there than you started with. You just don't have the summation of X2 that was there before, plus the X2 that you added because you had to use some of it. But the X2 actually increases. That's why that one's false. H2X decreases. No, if you shift it to the right, H2X gas is going to increase. Right, so that's false. And D and E can't be right, either one of those. So that was 9. How about 10? Addition of argon to the above system. What if we add argon gas to the system? What happens to the system? Well, the pressure increases, yes. But argon's not in the reaction, right? There's no argon in there. So increasing the pressure doesn't, by adding argon, does not change the concentration of either reactants or products. And in order to get a shift, the concentration has to change. Right? So adding argon has no effect. All right, that was 10. Let's see, how about 11? Which of the following statements is true? So we have to consider each statement independently. When two opposing processes are proceeding at identical rates, the system is at equilibrium. That's true. When the forward reaction rate is equal to the reverse reaction rate, you have equilibrium. That's definitional. So we would write it something like that. That's K1 and K minus 1. So forward and reverse rate are equal. This one equal. That's equilibrium. B, catalysts are an effective means of changing the position of an equilibrium. Do catalysts change equilibrium? Equilibrium position. Well, okay. A catalyst only changes the rate of the reaction. It does not change the value of K. Right? So by adding a catalyst to a reaction, you speed it up, but you don't change which way it moves. You don't change the equilibrium position either. So that was false. C, the concentration of the products equals that of the reactants and is constant at equilibrium. Well, no. You can have equilibrium with unequal concentrations, right? That's the whole purpose of the K, right? If the K is very large, then the concentration of products is a lot greater than the concentration of the reactants, and vice versa, right? So you don't have equal concentrations doesn't mean equilibrium. Equilibrium is established by the system itself, and it could be anything. So that was false. Let's see. Here we go. An endothermic reaction where delta H is positive shifts toward reactants when heat is added. Right? So if we have reactants yields products, then where is this term going to go? It's a reactant. Right? So by drawing that little diagram, it's easier to answer the question. Will it shift toward the reactants when heat is added? Now, if you add heat, you're adding reactants, so it'll shift to the products. Right? So that statement is false. And none of the above statements is true. Well, that one's false, because we found one that's true. The very first one. Okay, let's see. What if how about number 20? Now we can come back to any of these that I've skipped. I mean, if any of them are giving you problems, we can talk about any of those that I've skipped. But I've gone through this ahead of time and I've looked at them and said, these are probably the most important ones to cover right now. So I'll do those, and then we can come back. So number 20. So this was a reaction that we're allowing to come to equilibrium. That's a solid. This is a liquid. And here's our gas. And the delta H for this is 43.4 kilocalories per mole. So what's a calorie? We see calorie plastered all over our food products, but nobody ever bothers to define what a calorie is. Well, a calorie is an older version of heat content, as opposed to what we've been using in this class all along, which is joules. That's an energy unit. But calorie is defined, 1 calorie is equal to the amount of heat required to raise 1 gram of water 1 degree centigrade. That's it. Now, the calorie you see on your food products is not a calorie. It's a kilocalorie. Sometimes they call it a big calorie. And that's little c versus big C. All right, so the calories on your foods are 1,000 times bigger than that. All right, that's not part of the question. I just couldn't resist. Okay, the mass of this compound in the bulb could be increased. So what are the conditions that will increase HGO? Right. Conditions for increasing HGO. Well, let's look at the possibilities. Remove some of this. Now, if you remove mercury, it's a product, right? So this is going to decrease. Right? So that's not the one. That's false. Reduce the volume of the bulb. Decrease volume, which increases pressure. Okay, so in this case, it might have an effect because we have a gas involved, right? So you have 1 mole of gas here, no moles of gas over here, right? So if you increase the pressure, it's going to move back this way, right? Going to consume some of that to produce some of this. So that one is true. Adding more mercury. What happens to the equilibrium position when you add mercury? Well, let's look at the equilibrium expression. Right? K equals, that's it. Because that's a liquid and that's a solid. So the equilibrium constant says that the only factor that's important is oxygen. So if you add mercury, it doesn't change the concentration of mercury. There's no shift at all. So that's false. Increase the temperature. Increase temperature. What happens to increase temperature? Well, we have to look. This is a positive, so it goes over here as a reactant. If you increase the temperature, you're going to increase this factor and drive the reaction that way. So that decreases. Right? So that one doesn't work either. And then the last one is remove some oxygen. If you remove oxygen, you're going to shift the reaction that way. Right? Take some of that away. You're going to consume some of this to make more. So that's false also. The only true statement in there is B. All right. Okay. Take the shine off of that board. Okay. So let's see. Let's do 21 also. We're doing on time. Okay, we got over an hour left. That's good. So at 500 K, 1 mole of gaseous ONCl is placed in 1 liter container. All right, so the temperature is equal to 500 K. Let's see, let's get the balanced equation in here. Here it is. This is our equilibrium system. And these are all gases. Let's see, 1 mole of this is placed in a 1 liter container, right? So we have 1 molar as our starting concentration for that. And that's it, right? So we know which way the reaction is going, to the right. And it says at equilibrium, this compound is 5.3% dissociated. So 5.3% of that becomes products. And the question is, what's the K? All right. So we know this is an initial condition. Those are initial concentrations. So there's 1 molar there, 0 there, 0 there. We know that the change is going to go that way. So we're going to add some of that. Right? Well, if we say this is X, and this is 2X, and this loses, same as that one. So that's minus 2X. But we're also given information on how much of it actually dissociates. At equilibrium, 5.3% of this has been dissociated. So we may not even need those unknowns, because it tells us 5.3% of that becomes this. Right? So 5.3% of 1 is what? .053. Oops. Yeah, 0.053 of this is lost. This is equal to 0.053. So this is 5.3. This is only half of that. 0.0267. There we go. So if we lose this much, how much do we have left over? Well, just subtract that from that. Right? So I can do this in my head. 4, 9. Is that right? Yeah. Okay. So the real trick to this one is interpreting the 5.3% dissociation, because that tells you the equilibrium concentrations. And then all we have to do is plug those into the formula where it's this one squared, this one to the first power, divided by this one squared. So we just put this one, square it, and then put this one to the first power, and then we put what's left over. Oops, hardly read that. Square that. Right. So we just need to do a calculation. There's my calculator. Okay, 0.053 and square that one. Just have to find it. There it is. And then 0.0267 times, and then 0.947 squared. And divide that in. So, where am I going to write this? I'm going to write it up here. K equals 8.36 times 10 to the minus 5. Wow, is that one of our choices? Close. You know what I say. In the multiple choice, you may not have the right answer. Give the best answer. Closest answer to that one is 8.3 times 10 to the minus 5. You know what I think happened was I should have rounded this off to 7. That would have given me 8.3 and the answer that's in the review document. All right, that was 21. Okay. Let's see. I got 24 identified. I don't remember why. So let me look. 24. Is not, well, okay. It won't take long. We just have to set it up right. This is a word problem where you have to write the equation from the word problem. Nitrogen gas reacts with hydrogen gas. So 24. I guess we should do this one. Nitrogen gas reacts with hydrogen gas to produce ammonia gas. Right? That's not balanced. Right? 2 nitrogens, 1 nitrogen. There we go. Nitrogen's covered. 6 hydrogens, so we need a 3 here. Now we're balanced. Let's see. At 200 degrees, so temperature equals 200 degrees centigrade. And starting conditions. So we have, initially we have 1 atmosphere of nitrogen, 2 atmospheres of hydrogen, and no ammonia. Those are initial conditions. Okay, then we have a change and we have an equilibrium. So what else are we given? At equilibrium, the total pressure is 2.2 atmospheres. And the question is, what's the partial pressure of hydrogen at equilibrium? So the total pressure of all the gases is 2.2 atmospheres. Okay. Let me see. I would be inclined. Well, let's stick to procedure and see what happens. We know the reaction's going this way, simply because there's no ammonia here. So we know that we're going to produce some ammonia. Trick is choosing our unknown correctly. So if we want to solve for hydrogen, if we make that X, what is this one? Well, if we say that's X and we want to change it to ammonia, then we need the ratio of ammonia plus hydrogen, which is 3, 2. So this is going to be 2/3 X. Okay? And the ratio here is 3 to 1. So for every 3 of these, you only need 1/3 of those. Okay? See, I need some room. So let me put this up here. P total equals 2.2 atmospheres. Okay. So this would be 1 minus 1/3 X. This would be 2 minus X, which is what we're looking for. Actually, I probably made it harder than it needs to be. And this would be 2/3 X. So we don't even have to use the equilibrium expression. You know why? Because Dalton's law of partial pressure says that one plus that one plus that one equals 2.2. Okay? So it's kind of tricky. So if we say 1 minus 1/3 X plus 2 minus X plus 2/3 X equals 2.2. Then if we solve for X and subtract it from 2, we have the partial pressure of hydrogen. All right. So in the interest of time, X turns out to be 1.2 atmospheres. And then 2 minus X is equal to 0.8 atmospheres. So that's the equilibrium concentration of hydrogen under these conditions. Okay? That was 24. And let's see, 25. Okay. 5. Let's see. And we're okay. So our reaction is similar. That's supposed to be an N. And 2 ammonia. Okay. The equilibrium concentration of ammonia is 0.55 moles per liter. And it gives you the temperature. But I don't think we need the temperature because it's not changing. So what's the K? That's the question. Right? So we're using molarity, so this is a KEQ, not a KP. All right, if we know that, we also know initial conditions. In 1 liter, each of these, so there's 2 molar, 4, oops, nope, turn that around. Hydrogen is 4 molar. Nitrogen is 2 molar. And ammonia is 0 to start with. All right. So what's the value of K? Well, once we find out what these values are, then we plug them into this, and this, and this. Okay. All right. So we know that we're going to produce some of that. But let's make this one X. We're going to lose X of that one. That makes it easy. Then we have 2X of this. And we're going to lose, if we lose X of this, then we lose 1/3 of this. No, we use 3 times that. There we go. Right, 2, 1, 3. Okay. Actually, nobody corrected me. We don't need to use an unknown here because we know, like that. Right? Isn't that what it said? Equilibrium concentration of ammonia is 0.55. Yeah. Okay. So that means we had to lose 0.55 from here. And we had to lose 3 times 0.55. Excuse me. If that's 0.55, then this has to be half of that. 0. What? 2. 7, 5, right? I don't hear any objections, so I think I'm right. So if we gained this much, then we lost half that much here, 2 to 1, and we lose. If we lose this much, then we lose 3 times that much of hydrogen. Right? So we lose 15, 20, 22, and 2 times 6 is 8. Is that right? 3 times this, 15. 1 and 21 is 22, and 2 and 6 is 8. Yep. Okay. So now, how much of this do we actually have left? All right, so we have 1 point, let's see, 527. Yep. And this one, 5, 7, 1, 3, right? Yep. Okay, so now we have our values, don't we? Ammonia, 0.55 squared. Hydrogen, 3.175 cubed. And nitrogen, 1.725 to the first power. Now let's see if I get the same result as the answer in the key. So 0.55 squared and 3.175 enter 3 power. Divide into that and 1.725. So I get two significant figures, 5.5 times 10 to the minus 3. Okay. It agrees with the key anyway. I think the way I worked it out in this 25. No, that's right. Yeah, okay. 25. Now let's go to 26. This is going to be a shift. Give your brain whiplash. So here's we're starting out with two equations, and we're going to use Hess's law to produce the third equation. And we want to know what would be the, how would we calculate the overall equilibrium constant for that reaction. All right, so let's start off with this one, 26. We have 4 coppers and oxygen yields 2 Cu2O solid. And that has a K of 1, K1. This one yields that plus 1/2 oxygen. And this one has a K2. And our target, the composite, the one we want to derive from these two, is this one. Okay, and then we want to know what's the K for this one based on those two. All right, so we've got to rearrange, maybe multiply times a constant in order to make these equations, adjust these equations so that when you add them, you get this one. All right, so first one. We want copper as a reactant. Okay, copper's a reactant. That's good. But we only need 2 coppers. Right? And there are no coppers in here, just that one copper. So this has to be taken in half. So that gives you 2 coppers, a half oxygen, and 1 copper 1 oxide. Well, what does that do to the K? Right? How does that change the K? Remember, when we multiply times a constant through the entire equation, that becomes the power of the K. Right? So now we change this one to 1/2 power. All right? All right, so that gives us 2 coppers and 1 copper oxide. But what do we have in these that we don't need down here? Let's see, we have copper, oxygen, copper 2 oxide we need to get rid of. We can't have copper 2 oxide. So now we have 1 copper 2 oxide on that side. So we need to flip this equation over to this form. And 2 oxide. Okay. Now, what does that do to this one? When you invert an equation, it inverses the K. So this is now to the -1 power, or 1 divided by K2. Okay. So if we're going to use this one and that one to produce this one, let's see if it works. Right? So on this side, we have 2 coppers. We have a half oxygen. And then we come down here. We have a copper 1 oxide and a half of an oxygen. Now on the other side, we have this one and then this one. Okay. Now, let's cancel and combine. Right? We've got one of these over here, one of those over there. They're gone. We've got a half one of these and a half one of these. That makes 1. Right? So those are right here. This one's right here. This one's right here. We have our equation, and we've modified these in such a way that now, how do you add those together when you add the equation? Well, you don't really add them. When you combine 2 equations using Hess's law, the equilibrium constants are multiplied. So it's this one times that one. So now the K is equal to this one, K1 to the 1/2 power times K2 to the -1 power. Okay? Now let's see which one of these fits that answer. Well, let's see. The first one doesn't. K1 times K2 doesn't work. K2 times K1 to the half. They're getting there, but K2 is wrong. K2 to the 1/2 power is on top. Yep. No, that's wrong. It needs to be on the bottom. All right. It needs to be a different power too. D. K2 to the 1/2 power. Nope, that's wrong. So E's the only one left. K1 to the 1/2, yes, in the numerator. And K2 to the -1 is in the denominator. Right? So if we write it the way they have it here, then we would just say that like that. And that's your answer. So when you add those 2 together to get this one, this is the effect it has on the equilibrium constant for the new reaction. All right. That was 26. Let's see. Okay. We got about 45 minutes. How about, let's see. '28. We've done one like 28 already. N2O4 is 37% dissociated. That's kind of like the previous one. So I think that would be, we can come back to it. But since we've already done one like that, I'd like to maybe go to 29. See if 29 is a bit different. Yeah, 29 could give you trouble. Not because it's particularly difficult, but because it's a word problem, right? And word problems are specifically designed to confuse. So if we consider the reaction H2 plus I2 yields 2HI and a K of 44.8 at high temperature. If an equimolar mixture of reactants gives the concentration of the product to be, all right, so we're going to put in the same amount of this and that, and whatever it happens to be, but yeah, start with that there. Right. But we're also told that the concentration of the product is 0.50 molar at equilibrium. The question is, what's the concentration of hydrogen at equilibrium? All right, we've got that, and that's equal to, let's see, well, we're not told, right? If you go back and look at the, all right, here, we are given an indication. You would normally expect this to be a gas. At room temperature, that's a solid. And hydrogen iodide would be a gas. But we're also told that it's very high temperature. So that's a clue that they're all gases, right? We've converted this one to a gas. So that means the equilibrium expression will include all of those terms. Right, so we're going to have this one squared divided by this one times that one. Oops. There we go. We just need to find out what values do we need to put in there so that we can solve for the concentration of this one, right? That's going to be our unknown. So notice that if we do this, we have a certain amount. Yeah, we have a certain amount of this. And then how did we get this one? Well, we started with 0, so we had to add that much. It's the only way you can get it. So that means if this represents 2 moles, then the ratio 2 to 1 means these are half moles. So we had to lose this much and this much Okay. So what that tells us is this one is that. Okay. Now, I think I can use a little trick. Actually, we want to know what this is right here. And these are equal, right? So let's make another substitution. Let's say that's y and that's y. Then we can put in this value and this value for here and here. And this value for here. This is just a way of shortening the agony. So this will be that squared times this times that. Right? So this is y squared actually. So now if we solve, y squared equals, what's 0.5 squared? 0.25, right? Or is it 0.025? 0.25. So this is 0.25 divided by 44.8. Which says it's 5 point, rounded off, 6 times 10 to the minus 3 molar. So that's squared, right? So we need to take the square root of that, right? And that becomes square root 7.5 times 10 to the minus 2. And by making that simple substitution, we don't have to do an extra calculation. So we could have put these values in there and solve for x, but we needed to know the whole value anyway, right? So we just made another substitution, and then we don't have to go back and do that calculation. And let's see, is that one of the answers? Yeah, that's E. Okay? All right, so that was 29. Let's see. $30 is just calculating Q. You know how to do that. You just need to write your equilibrium expression and substitute the concentrations that are given you. So I don't think we need to do 30. $32 looks like it's fairly straightforward also. Right? You just build your ice table. Yeah. We can come back to it if we need to. 33. It has a few extra steps in it, so let's do that one. Okay. So here's what we're given. We've got a temperature of minus 80 degrees C. the reaction is N2O4 yields 2NO2 there. And the K for that reaction is 4.66 times 10 to the minus 8 at that temperature. So we introduce 0.047 moles of this one in a 1 liter vessel. So that means it's 0.047 molar. And none of that. So that's our initial. So we're going to have a change and then an equilibrium. Right? And the question is, what's the total pressure? So what we need to know is, let's see, volume is 1 liter. So this is shaping up to be not only an equilibrium problem, but an ideal gas equation problem. What we have to do is find out what these values are. Yeah, equilibrium, because both of these are gases, and this one needs to know the total number of moles to give you the total pressure. We've got that value, we've got this value, we've got that value. To solve for this one, we need to find the total number of moles. Okay? So the change then is going to produce, we're going to lose some of that, and we're going to make some of that. Right? So this is 0.047 minus x, and this is 2x. And then the equilibrium expression for that, K, is 4.66 times 10 to the minus 8 equals this one, 2x squared, divided by this one. Okay? So we need to solve for x. The reason we couldn't do the same type of substitution for this one as we did before is because these are not equal values. We can't say y. Before we had x minus 0.25 and x minus 0.25, they're equal, so we could do a substitution. This one we have to solve for x. And let's see, am I going to have to do a quadratic? We're going to assume that okay, see how small that is? That means we're not going to produce a whole lot of this. That means this term right here is much, much, much smaller than that one. So what that means is we can say, throw that one out and just keep this one. So then solve for x, and in the interest of time, x is equal to 2.34 times 10 to the minus 4, I think. Nope, 5. Excuse me. All right. So we subtract this from that one. And that gives us well, I didn't do individual calculations. This one minus that one would be, well, I guess I better do it. So 0.047 and 2.34 exponent minus. So this one is equal to 4.70 times 10 to the minus 2. And this one is 2 times that. .68 times 10 to the minus 5. You know what? That's not right. .34 exponent 5 change sign 0.047. Okay, I did it right. Okay, so this is the that's the molar concentration, molarity, and we've got a 1 liter volume. So 1 liter times that cancels out the volume, and this is actually the moles. Everybody follow me on that? Since the volume of the container is 1 liter, if this is molarity, then 1 liter of it has that many moles. Right? So we can say this plus this is the total number of moles. So N equals this one plus that one. And it's basically this one. 4.70 times 10 to the minus 2. All right. So that N is times 0.0826. What's the temperature? 273 minus 80. 193. Okay. Volume is 1. So the pressure is equal to the solution of that problem. I think that's 0.8206. And so I get 0.745 atmospheres. Yeah. Must be a rounding error because the answer in the key is 0.74 atmospheres. Any questions about that one? Besides the mess? Okay, we got about a half hour left. Let's see. 34. Okay. We could do 34. I want to add a twist to 34. So for this equation, we allowed this to decompose to these gases. All right. Total pressure in the vessel after the reaction is 2.63 atmospheres and a temperature of 500 degrees C. So what's the KP? First of all, the KP doesn't have anything to do with that. KP is this. N2O and H2O squared. Okay? Well, actually, that's not even right. It's KP. You want the partial pressure of N2O times the partial pressure of H2O. That's KP. All right. 34. Right. Now, the first assumption we have to make is this ammonium nitrate completely decomposes, which gives us just these two gases in the environment. So first of all, if that's the case, then the ratio of this one to that one is equal to 2 to 1. So you should have twice as much of this as you do of that. And which means that according to Dalton's law, 2 plus 1 is 3, so 2/3 of the pressure is going to be due to this one, and 1/3 of the pressure is going to be due to this one. But if we set the total pressure is 2.63, right? Atmospheres. And that's equal to the partial pressure of N2O plus the partial pressure of water. But the partial pressure of water should be twice what N2O is, right? This is Dalton. So if that's the case, then the partial pressure of N2O is 1/3 of this, right? That's equal to 3 times this. So the partial pressure of N2O is equal to 2.63 divided by 3, which is 0.8. 0.8. 3, 4. I can't do that in my head. There was a time. 877 atmospheres. So that means that the partial pressure of water is 2.63 minus 0.877. .75. Okay, so now we have the values for this one and this one. We can plug them in here. And N2O is this one. Water is this one squared. So let's see what that gives us. Square that one, and then 0.877 times, so I get 2.69. or round it off. .7. Let's see. 2.63. Okay, we can have three significant figures. All right, so that's the KP. Now the twist I want to throw in is, what's the K? So if this is the KP, 2.69, let's do this. If this is the KP, how is that related to the K? Well, the formula, I believe, is times R. Let's see. Useful information. I do it as much for me as for you. RT to the change of n. Okay. So it's the change in the number of moles of gas is the product number of moles minus the reactant number of moles. So in this case, we have 1, 2, 3. 3 minus 0. So n, that change in n is actually 3. And the KP we know is 2.69. That's our unknown. R is the one with atmospheres in it, because this has atmospheres in it, times the temperature in Kelvin, right? So that needs to be 273 plus that. That's 773 to the third power. So we just need to solve for this K. Let's take that one, and then we'll take this one, 08206, enter, and 773 times, take it to the third power, and then divide it into that one. And that gives us 1.05 times 10 to the minus 5. So that's the KEQ for that reaction. Let's see. Well, I don't have it written down in your document. I just wanted to add that in there as an object lesson in how to convert. Okay, we got 20 minutes. And I got a couple that are not in the review document I thought would be helpful. Let's see. Well, looking at them now, we've covered the topics. Maybe I'll do this one. Let's just do this one. So if we have an equilibrium system that's this, that's a gas, and this this. Okay? The Kp is equal to 0.604 at some temperature. So we have initial change, equilibrium. What are the initial conditions? Well, actually it tells us at equilibrium, the NO2 gas pressure is 0.520 atmospheres, and the NO pressure is 0.3 atmospheres. Then we want to know that one. Oh, that's too easy. That's way too easy. You got the Kp. All you need to do is write the expression, right? NO. Well, let's see. That's not right. Pressure. Pressure of NO squared times oxygen. Pressure of oxygen to the first power divided by pressure of NO2 squared. So what values do we know? Well, we know this one, and we know this one. So we just solve for that one. I thought this was going to be difficult. So let's square that one first. That's so we can multiply it times this one. And then we'll divide it by this one squared. So that leaves this one over here, and that one comes over there to the denominator. And that says the equilibrium partial pressure of oxygen is 1.81. Okay? That was way too easy. Should have made that one harder. Are there any that we skipped that you'd like to go back to? You're probably getting bleary-eyed by now. If you haven't fallen asleep. It has that effect sometimes. Let's see, which one did I skip that we might want to do? Might have just enough time to do number 36. So 36 is based upon the reaction. This yields this. And the K is equal to 7.5. They're both gases. So the expression here is going to be that one. This is a K. Yeah. So this is KEQ. This is not partial pressure. To the first power divided by this one, second power. Okay, what are we given? 2 moles of NO2 are placed in a 2-liter container. Okay, 2 moles in a 2-liter container. Right, so initial, this one is 1 molar, and that one's 0. So the question is asked, the concentration of N2O4 at equilibrium. So that's the one that we're aiming for. And it will be here. So we need to find out what this one is. All right, so we know we're going to produce some of that. That means we're going to lose 2 of these. Right? If we produce 1 of those, we lose 2 of these. So that means this is our X value. That's good, because if we solve for X, we got our answer. And this is 1 minus 2X. Okay? So let's see what we get up here. If this is X, right, put it in here, and this 1 minus 2X squared is equal to that value. Now, right off the bat, you see we're going to end up with a quadratic equation. Here's the problem. We cannot estimate, we can't assume that X is very small, because it's not. With that value, we're going to produce a lot of this. Right? So we're forced to either solve a quadratic equation, or one other possibility that I didn't mention in the lecture was the method of successive approximations. Right? So how does successive approximations work? Well, successive approximations works by doing just what I said not to do. Set that one equal to 0, and then going back and plugging in the X in this time and solving for the other X, and then going back with your new answer and doing it again. How do you know when to stop? Well, there are 2 possible ways. You either do the 5% rule and check your answer, or you keep doing it until the answer becomes almost the same every time you do it successive, right? It just becomes asymptotic to the axis, okay? I think the quicker way would be to use the quadratic equation. Sometimes successive approximations is more efficient, and that works really well if you have a lot of computing power, because some of these expressions can end up with powers. You could have 3, 4, 5th order polynomials, right? In that case, how do you solve those, right, without a computer? Well, you either get the computer to use some solution that probably gives you 5 possible answers if it's 5th order, or you do successive approximations and the computer can do that too. It just crunches your numbers. But in this case, we do have a solution for it. So let's resolve this into a quadratic. Right? So this would be 1 times 1 is 1. 2x times 2x is 4x squared. And that's a negative times a negative is a positive. And then that times that is minus 2x plus minus 2x, which is a minus 4x, which is equal to 7.5. Oops. Forgot that term. So now what do? Well, you take this group over here and go over there. So 7.5 times that minus 4 times 7.5, which is 30, minus 30x, and then 4 times 7.5, which is 30 again, but this time it's plus 30x squared equals x. Remember, quadratics have to have everything on one side equal to 0. So this comes over here as a minus. Minus 31x plus 30x squared equals 0. Right? So for our quadratic equation, this is the A term, this is the B term, and this is the C term. And remember, your solution is x equals, I have it on the back of my calculator, minus b plus or minus the square root of b squared minus 4ac all over 2a. So you plug these numbers in there, and you get two answers. Right? So in the interest of time, 36. In the interest of time, it could be either 0.647 or 0.386. Those are the two answers that we got from that expression. So which one is right? Well, if we say let's take this one. And if we plug that back in here to find out N2O4, I always have to go back to the question. Concentration of N2O4. So that's what we want. So let's put 0.386 in here. And if x is equal to 0.386, what does that give us? No, that's not right. That was our x. That is equal to N2O4, 0.386. So what if we put 0.647 in there? If we put 386, then that means this would have to be this starts off at 1 molar, right? So if we put 0.386 in there, and we say that means that this had to lose twice that much. So 0.386 would be like 0.772 minus 0.772. Okay, that's doable, right? There's enough there to give you that much and make this. But if we said 647 times 2, that would give you a number greater than 1. And you subtract it from 1, you get a negative number. It can't work. Right? So that's why 0.386 molar for that concentration. That's the problem with quadratics. You have to decide which answer is the correct one. Okay, we only got 5 minutes left. So we'll see if you have any questions, any concerns. I've only received 2 lab reports so far on the first lab, which was molar mass by freezing point depression. All right, so I'm missing 3 labs on that particular one. You want to get those in. The second one was what? I forget what the second one was on. Kinetics. That would have been the one where
Dr. Bly,
Yes. Who's talking?
I have to go.
Oh, okay. Go ahead.
Me, Steffi.
Yeah, that's
All
fine.
right.
That's fine.
Yeah. Okay.
So the second lab is on kinetics, which is the blue dye that we added bleach to and watched the absorbance decrease. That's your second lab. The third lab's not due yet. In fact, the second lab's not due until the third one. Well, actually, it is due because the third lab opened up last Thursday. So you need to get that in to me also. That's a formal report. The third lab is not a formal report. We talked about that on Tuesday. Okay. That's all I've got. So we say bye. We say bye. Is Isaac still there?
He says he's still there, but I don't see him. I ain't seen him all class.
Yeah, Isaac, you got to tell me you're there. I don't want to count you absent.
Well, bye.
Bye-bye. Are you there, Isaac?